In this lesson, we will solve a practical cache sizing problem using virtually indexed, physically tagged caches. We will compute the number of sets, the index bits, and the tag bits for a 64 kilobyte for WAY level 1 cache with 64 byte blocks using a 48-bit virtual address and 4 kilobyte pages. We will also check if an aliasing risk exists, and we will do this both mathematically and graphically. Here is the problem setup. Step 1. Compute the number of sets. Total lines equals cache size divided by block size. That is 64 kilobytes divided by 64 bytes equals 1024 lines. Sets equal total lines divided by ways. That gives 1024 divided by 4 equals 256 sets. The index bits are log base 2 of the number of sets, so 8 bits. The block offset bits are log base 2 of the block size 64, so 6 bits. The page offset bits for a 4 kilobyte page are log base 2 of 4096, which is 12 bits. In a VIPT cache, the stored tag is physical. If the physical address width is p bits, then the physical tag bits equal p minus index bits minus offset bits. That is p minus 14. If we assume a 48-bit physical address, then the physical tag has 34 bits. Now, let us visualize the virtual address bit fields. We draw a 48-bit bar split into 3 parts: virtual tag on the left, index in the middle, and offset on the right. The rightmost 12 bits are the page offset. Those are the only bits that are unchanged by translation. Our offset is 6 bits. Our index is 8 bits. That means 6 of the index bits are inside the page offset, but 2 of the index bits sit outside the page offset and belong to the virtual page number. Those 2 bits are the dangerous ones for VIPT because synonyms can differ there. Next, a simple cache picture. In a 256 set, 4-way cache, the index chooses one of 256 rows, and the way is chosen by tag match. We will show an abstract grid to keep things readable. The VIPT safety rule is the index bits plus the block offset bits must fit entirely inside the page offset. This guarantees the index uses only untranslated bits. Here, index plus offset equals 8 plus 6 equals 14, which is larger than the page offset of 12. Therefore, 2 of the index bits come from the virtual page number. That creates a synonym or aliasing risk. Different virtual addresses that map to the same physical page can pick different sets. Let us see the aliasing visually. We will imagine 2 virtual addresses, call them V1 and V2, that differ only in those 2 dangerous index bits, but they translate to the very same physical page. Because those 2 bits select different sets, V1 and V2 go to different rows in the cache, even though after translation, they refer to the same physical block. That is the synonym problem in VIPT. How could we make this cache VPT safe? We must ensure index plus offset is less than or equal to the page offset 12. With a 64-byte block, the offset is 6, so the index may use at most 6 bits. That means at most 64 sets. Keeping 4 ways and 64 sets gives a maximum VIPT safe capacity of 16 kilobytes. Alternatively, keep 64 kilobytes by raising associativity to 16 ways, so the sets drop to 64. Summary: number of sets is 256. Index bits are 8. Block offset bits are 6. With a physically tagged VPT cache, the physical tag bits equal p minus 14, which is 34 if p equals 48. Because 8 plus 6 is greater than 12, aliasing risk exists. We demonstrated this graphically with the 2 dangerous index bits.